The screencast is an introduction to trees. Trees are a special type of graph that reduces the complexity significantly because it's very restricted. But it's still useful in a large number and a wide variety of situations. Some of them are file systems, family trees, evolutionary trees in biology. It's very useful data structure in modern biology. Language processing and expression evaluation and compiling. Coding theory, and efficient search and data storage. There's lots of variations of different types of trees that are used in data storage. So what is a tree? A tree is a connected, undirected graph with no simple circuits. This actually is not all that restrictive, other than it means that there's no circuits in the tree. So we're going to be, in this course, we're going to restrict it a little bit more. We're only going to look at rooted trees. So in rooted trees, there's a special vertex called the root, okay? And every edge is directed away from the root. So typically, these trees are sort of drawn upside down. So here we have the root at the top of the tree, animal, and then we have the branches, reptile and mammal, and then in this particular tree, sort of a simple evolutionary tree, things get more restricted as we go down the tree. So let's start to introduce some of the terminology. There's quite a bit of it. We have our root here. If we take a simple path to some vertex, say this one, the level of that vertex is going to be the length of the path. So the level of this vertex is 2. The level of this vertex all the way at the end is 3, because it takes 3 edges to get there. The height of the tree is the maximum level. So in this case, the maximum level is 3. And then we have a lot of terminology. If we think about some simple path, then, so let's take this path here from the root to this node, to this node, to this node. We can talk about a node being a child, or a vertex being a child of another vertex, if it's the next vertex on the path. And the parent of a node, or if we look over here down this path, for instance, the parent of a node is the previous vertex in the tree. And if we have a node, say for instance, if we took this node, the parent-child relationship also indicates what we expect in terms of what are the ancestors, say, of this node. Well, it's this node, and this node. So it's anything backwards on the path. And what are the descendants? Well, the descendants would be, say, of this node, would be anything below it in the tree. So anything you can take a path from the node. And that's exactly what you'd expect from the normal English meanings of those words. So I already talked about ancestor and descendants. We also use other English language words that mean exactly what you'd expect. We can talk about siblings. So for instance, if we talked about this particular node, these two children would be siblings of one another. If a node has no children, then it's called a leaf or a terminal node. If it has some children, then it's called an internal node or a branch vertex. Probably one of the most important things to remember and to learn about is what's called a subtree. So a subtree, say at this node here, is that node plus all its descendants, and along with their edges. Okay, so the subtree of this node would include this vertex, this vertex, this vertex, this vertex, this vertex, and this vertex. So there'd be, in this subtree, there'd be 7 vertices altogether, and it also includes the edges. So there'd be 1, 2, 3, 4, 5, 6 edges. So this picture over on the side is pretty good in terms of illustrating sort of the major components of a tree. You've got the root node, then you have internal nodes, and then you have leaf nodes. Sometimes the root node is considered an internal node, but not in this picture. So we're going to focus on an even more specialized kind of rooted tree, and that's a binary tree. And that's where each vertex has at most 2 children, designated as left and right child. So if a vertex has 1 child, you still designate it as either the left or right child, but not both. So for instance, if I look in this example, 2 is the root, 7 is the left child of 2, and 5 is the right child of 2. 9 is the right child of 5, 4 is the left child of 9. So again, it's exactly what you'd imagine it to be, and it's as you look at the tree. So this is 7 is the left child of 2, and this 2 is the left child of that 7. Now we have a special kind of tree that will use a little bit, but not a lot, but you should be aware of it because it does come up very importantly in some sorting algorithms, or a variation of it, and that's called a full binary tree. And that's where all the leaves are at the same level. Okay, so on this tree, all the leaves are at the level 3, and it has a height of 3. And what makes it somewhat interesting, if you look at it, is how many internal, if I count the root as an internal node, right, there are 7 internal nodes and 8 leaves. Notice again, this was level 3, so the 8 is 2 to the 3, and the number of internal nodes is 2 to the 3 minus 1, so that's 7, and then the total number of nodes is going to be equal to 15. We'll talk about this more in later classes. So another way to look at, or another way to state what I just said, if you just count the internal vertices, then the tree has 1 more leaf than the number of internal vertices. The number of leaves is 1 more than the number of internal vertices. And so the total number of vertices is 2 times the number of internal vertices, plus that extra 1. If you have a binary tree of height h, right, well then you know its terminal vertices have to be less than what they would be in the full binary tree. And as I said, in the full binary tree, they're 2 to the height of the tree, so the number of terminal vertices has to be less than 2 to the h. You should convince yourself about this. Think about what we've learned about counting and multiplication in terms of the levels of the tree and the number of nodes at a particular, or vertices at a particular level. I won't talk about M-array trees too much in this class, but they are very important in storage. That's M-array stands for something, basically could be any number. We're going to be focusing on binary trees, so that's when m is equal to 2, and we won't worry about any of this, but I just put it here for completeness. And of course, as I already mentioned, the binary trees are ordered rooted trees. And again, that's just something I want to emphasize for you to keep in mind. So here are a few practice questions for you to look at and help you prepare for the quiz. And so take a few minutes, think about those questions, and then come back and I'll indicate some of the answers for you. So what is the parent of canary? Well, here's canary right down here, so the parent is bird. What are the ancestors of horse? Well, horse is here, so horse's ancestors, again, take the path back to the root. Equine, mammal, and animal are the ancestors of horse. What are the children of mammal? Well, the children of mammal are equine, bovine, and canine. And what are the descendants of reptile? Well, now we basically get everything that's below reptile in the tree. So we get lizard, salamander, snake, bird, canary, and tweety. What is the height of the tree? Well, we need to look for the longest path. And so this is the longest path. It has length 4, so that means the height of the tree will be 4. What's the level of snake? Well, snake is right here, and the length of the path from animal to snake is 2. So snake is at level 2. And what are the siblings of snake? That's a lizard and bird.